So today I will title it Our Three Amigos Needs a Fourth Mouseketeer. Alright. We will not beat around any bushes. Here is the fourth Mouseketeer. The fourth theorem of showing two triangles are congruent. So the book calls it a postulate. I'm going to call it a theorem. It's not exactly potatoes. I don't understand why they insist on calling it a postulate, because we can prove it. So here's what it says. If you have two right triangles, two corresponding sides are congruent. Those have to be the hypotenuse and the leg. Then the triangles are congruent. So let's look at an example. Here we have two triangles, and we will establish that these two triangles not only look like right triangles, but they are right triangles because of that. And notice they each have a corresponding side, the longest side, aka hypotenuse. Hypotenusi are congruent, and the two legs are also congruent. So these two triangles then would be the same. Notice, if you think about three letters, side, 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 side angle, side angle, side angle, it looks like, if you do use those type of acronyms, that we have angle, side, side. And I'll explain why it's not that case, why in actuality we are looking at side, side, side. All right? Let's just take this particular triangle. If we know this side here is, say, 10, and again, I'm just picking a random number, and this side is 6, then I can do math to figure this side out. Meaning, you were once taught something about a Pythagorean formula, and it said that a squared plus b squared is c squared. Notice how there's three variables, and they each related to one of the legs of a triangle. In this case, c was the longest side, 10. So if I were to solve this problem, and I'm not going to, but I could plug in 10 here, 6 here, and I can solve for a. And by the way, you'll get 8 if you do it. But whenever you fix two of these sides in a right triangle, there's only so much left over for that third side. So it looks like we've got just two legs, but we actually have three legs because it's a right triangle. All right? If it weren't a right triangle, then all bets are off. So here goes a quick proof, and then just a quick summary. So here's a diagram, but this diagram is not accurate by any stretch of the imagination. So though it does look like Pac-Man, kind of, I don't know. I'm going to redraw it over here so it looks more accurate. We are given, I'm going to mark it in this diagram, we'll go back and look at the diagram, that those angles are perpendicular. Therefore, there must be 90 degrees. So we can clearly see that we have two triangles that just might be congruent. So we might be able to use the HL theorem on this problem. All right, let's go back and look a little bit closer. And so again, we're given the perpendicular business, and we need to prove a couple sides. All right, now if I look at these two triangles, I still need a hypotenuse and a leg congruent. Well, lo and behold, the hypotenuse is shared between them. And these legs here happen to be radii of a circle. So voila, we seem to have HL in the pocket. And our goal is to prove XY and XZ. So let's go find those. So there is xy and there is xc. I need to show those two sides are congruent. Well, the CPCTC does that. Okay, so now that we've kind of planned out the proof, let's go ahead and dive in. I'm going to do this as a flow chart. The book has done a few of them, and you may enjoy this type of proof more so than the others. All right, we have two sets of perpendicular lines. Let's jump off of that. And if the lines are perpendicular, then angle OYX is right. And angle OZX is right. All right. Now that we know that OYX is right, how do we know that? You know, what's the reason? Well, they gave to us here perpendicularity. Whoops, didn't mean to scribble that out. Perpendicularity. So let's come back over here and say definition of perpendicular lines. And same goes for this, definition of perpendicular lines. All right, now let's jump to our next conclusion. If those are right angles, then we have triangles that are right triangles. So OYX is right. And triangle OZX is right. All right. Again, why would this be true? Why would these two triangles both be right triangles? Well, they got a right angle on them. So that's the definition of right triangle. Definition of right triangle. All right. Now here's where the creativity of these types of proofs come in. Now we need to bring in that the hypotenuse is in the leg, and you can like put these little shapes wherever you want. So I'm going to come up here and I'm going to say the hypotenuse OX is congruent to itself. Okay. A little bit too high there. Let me drag that down a little bit. And then the reason for that is the reflexive theorem. Then I'm going to come down here, and remember those radiuses, OI and OC, we got to get those equal to each other. And radii are congruent. And of course that means radii in a circle. All right, well now these four things, right? So this, and this, and then this, and finally, my last statement all come up to tell me that triangle OYX is congruent to triangle OZX. And this is because of HL theorem. And then if the triangles are congruent, then any corresponding parts. So now we then do a little arrow like this. Kind of ran out of space. So I can just sneak it in here and say YX is congruent to ZX. 5 letters, people. All right, in summary, to use the HL, you need to prove 3 things. Number 1, you have a right triangle. If you don't see a right triangle, you can't use HL. Because a right triangle means we have, a right angle means we have a right triangle. then you have to show that the hypotenuse is congruent to the hypotenuse and the leg is congruent to the leg. So even though it looks a little bit different because it just uses two letters, there still are three things that you need to kind of establish whenever you use the HL postulates. Good luck in your homework. The last one of chapter 3.